So in this section, we're going to talk about how to find absolute extrema. So we have had relative extrema before, where we found relative maxes and relative mins. So now we're going to work on finding absolute maximums and absolute minimums. And the first type of function we're going to look at is a continuous function where we're going to chop the function off. So we're going to only look at a portion of the function between two endpoints. So what that first property says is, if I have this function here that I am essentially cutting off a little bit, so I have cut this function off here at this a value and at this b value. So even though the function itself goes on forever, we're only looking at the portion of the function in between those two endpoints. And so what that extreme value property says is that if you do have a closed interval like this one, then the absolute max and the absolute min is always going to occur at either one of those endpoints or at a relative max or relative min. So we can see that illustrated in this graph here. If we look for the absolute maximum, meaning the highest point that that curve reaches in between A and B, we can see that the absolute max would be here. That's the highest point if we stay within A to B. And if we look at where the absolute minimum would be, it looks like the lowest point would be somewhere right here at that dip in the graph. So we know that when we're looking on a closed interval, that our absolute max and our absolute min is always going to occur at either one of the endpoints, that A or B, or at an absolute max or absolute min that lies between A and B. So let's take a look at an example where we'll actually find that absolute max and min. So there are some steps there written in your notes on what you needed to go through when you're looking at a closed interval. So essentially what we want to do is find all of the locations where relative max or min might occur, which means finding the critical values from the first derivative. And then we also want to consider the endpoints of that interval that we've been provided. So let's take a look at this example. So we've got a function here where we've got a closed interval, so we only want to look at this function in between -3 and 0. And now what we need to know is, where are those critical values in between -3 and 0? So we find critical values the same way we always have. I'm going to find the derivative of this function. So the derivative would be 3x squared minus 3. And I want to set that derivative equal to 0, and at the same time I will factor out the greatest common factor of 3. And then I want to continue to factor that, or at least go as far as until you can see what the critical values are. So you might be able to see that at this point, but I'm going to go ahead and factor that x squared minus 1 as the difference of two squares. And now I can definitely see what my critical numbers are. They are -1 and 1. Now, one thing you got to remember right now, once you've found your critical values, is we need to keep only the critical values that are in that interval from -3 to 0. So I know -1 is in between -3 and 0, but my 1 is not. So this one is going to get omitted because it is not in that interval between -3 and 0. Now, sometimes you omit critical values and sometimes you don't. So you always need to make sure that you check. Okay, so we know what values we want to look at. What we're interested in is finding out, is this critical number, or are either of these endpoints an absolute max or absolute min, or which one is which? So to do that, what we're going to do is create a little table. I'm going to create an XY table where I'm going to determine what the Y values are for those three numbers. And the biggest Y will be my absolute max. The smallest Y will be my absolute min. So let me do my chart. So I've got an X value of -1, an X value of -3, and an X value of 0. So again, all I'm doing is putting in the endpoints of my interval. Those will always be included. And then any critical values that I kept because it was in the interval. All right, now we need to find Y values. And remember, to find Y values, we're going to do the same thing we always did when we were graphing and had to find Y values. I want to find Y values from the original function. So I want to use the original f of x to find my Y values. So if we start with -1, I want to put -1 into the original function. So I'm going to have -1 cubed minus 3 times -1 plus 2. So if I do that arithmetic, I end up with, let's see, -1 plus 3 plus 2 is equal to 4. So the Y value for -1 is 4. Now I'm going to do that same thing with -3 and with 0. So I'm going to run through the math real quick, and you can double check me. But if I replace -3 into my original function, everywhere I see an x, I end up getting -16. And if I take 0 and plug it in to the original function, everywhere I see an x, I get a Y value of 2. So now all you're going to do is compare those Y values. So my absolute max occurs at the point where I have the biggest Y value. So my absolute max is right here. There's my max because 4 is the biggest Y value in my list. And if I look for the smallest Y value, I'll have found my min. So -16 is the smallest Y value, so that's my absolute min. So if we write out what our answer actually looks like, then we would say that the absolute maximum of that function in that interval is at -1, 4, and the absolute min of that function in that interval is -3, -16. So several series of steps, but none of them are anything really new. So none of the calculus is new. We found derivatives, we found critical values before. So it's just a series of steps that you're going to do every single time, anytime you're finding absolute extrema on a closed interval. So let's take a look at one more example. I'll go through a little bit quicker. If you want to try to work ahead, that's great. So we're going to start with step number 1 being to find the critical values, which means I need the derivative of this function. So my derivative is 3x squared plus 6x. I want to set that derivative equal to 0 and factor out the greatest common factor, which in this case is 3x. So if I divide out a 3x, I'm left with x plus 2, giving me two critical numbers, x equal to 0 and x equal to -2. Once I find my critical values, remember this is a crucial step that you remember to check those critical values against the interval that we were given and throw out any that do not fit between 0 and 2. So that means that I get to throw out the -2. So that leaves me for my testing for my XY chart, the only values left are the x equal to 0. So 0 goes in my chart, and my endpoints. And my endpoints are 0, which I already have in my chart, and 2. So my 2 will go in my chart. And now I want to find the y values. So to find the y values, I'm going to plug each one of these x values into the original function. So I want to find f of 0, which when I replace each of these x's with 0 is just going to leave me a 1. And I want to find f of 2. So everywhere I see an x in the original function, I'm going to replace that with 2. And if I do that arithmetic, I end up with 21 for my y value. So in this case, where I only have 2 x's in my chart, one of them is going to be the max, one of them is going to be the min, and you just compare the y values to see which one is which. So for this problem, my absolute max is going to be the 221, and my absolute min will be my 0, 1. So on closed intervals, these are the steps that you follow each time. So nothing too terribly difficult or complex about it. But now we need to turn our attention to intervals that are not closed. So a couple of different things here. If an interval is not closed, when I'm taking a look at what that looks like, I might have a graph, say, excuse me, that would be something, let's use a parabola here. So let's say that I have a parabolic graph that goes on forever and ever. And instead of cutting it off in 2 places, like I did in the previous graph, this time I cut it off only 1 time. So let me stick some axes in there. So there's my parabola, and say that I create an endpoint here at -4, but I leave the other endpoint open. So this time we're looking at a problem like this. So if one end goes on forever and ever, in this case the one I've drawn, it's going to go up forever. I'm never going to have an absolute max for that function because it climbs forever. But I would have an absolute min. And just like before, that absolute min is going to occur at a critical number in that interval. So there would be my absolute min. Now, the only difference is that I'm going to have one, not the other, if I only have one critical value within that interval. So what we're going to do to test whether that one critical number is an absolute min or an absolute max is we're going to use concavity to tell us. So notice in this drawing that I made, this graph is concave up, so that lowest spot was an absolute min. Now what tells us about concavity is the second derivative. So we're going to use this second derivative test to tell us whether the critical value we're looking at is an absolute max or an absolute min. So the absolute max is going to occur when my second derivative is negative, because remember, when a second derivative is negative, it means that my graph is concave down. And so if you just draw a picture of something concave down, notice that it naturally creates an absolute max. And if I test my second derivative and get a second derivative that's positive, we know that a positive second derivative means that my curve is concave up, which is naturally going to create an absolute min. So let's take a look at an example. Let me show you how this works. So you will know the difference between these ones and the ones that I did previously is by the interval. So notice that in this example number 3, what my interval looks like. My interval is an open interval that starts at 0 and goes to infinity. So I only have one endpoint in my interval. Okay, the first couple of steps are the same as they were in the previous examples. I need to determine the critical values that fit this interval. So that means calculating my first derivative, which would be 4x cubed minus 12x squared, setting that equal to 0. and I'll factor out the greatest common factor of 4x squared, and that leaves me an x minus 3. And so I have two critical numbers, x equal to 0 and x equal to 3. So just like in the previous examples, you need to pause here and eliminate any critical value that isn't in the interval provided. So remember, my interval provided was x had to be strictly greater than 0. I don't have the or equal to under my greater than. So that means 0 is eliminated. And the only critical number that I have to work with is 3. And I don't have an endpoint, because even though my endpoint up here is 0, it's not greater than or equal to. So that 0 is not included. So here's why I have to have some other method of determining what 3 is. In the previous examples, we created an XY table, and then we compared our Y values. And the biggest one was the max, the smallest was the min. But the problem here is I only have one X. So whatever its Y value is, I don't have that Y value to compare to anything else. So I can't tell based on its Y value whether it's a max or a min. So here's where it changes when I'm dealing with an open interval. What I need to do next is find my second derivative. So here's where the second derivative test comes in. Now, when I do my second derivative, I'm going to work off of this first derivative because I don't want to use the product rule. So my second derivative would be 12x squared minus 24x. And now I don't need to set this equal to 0. I'm not looking for second order critical values. What I want to know now is if I plug this one critical value from my first derivative into the second derivative, will I get a positive result or will I get a negative result? Now, if I have a calculator handy, I could just plug my 3 into that form of my second derivative. Or if you do want to factor it, sometimes that makes the math easier. So if I factor out a 12x, now I can tell that if I plug, grab a different color here, if I plug 3 into that front factor, that's going to be positive. And if I plug 3 into that second factor, that's also going to be positive. So I know that when I plug 3 into that second derivative, it equals a positive value. So I don't really care what it is, just whether it's positive or negative. Okay, so think about what that tells you. A second derivative is positive. A second derivative being positive implies that my curve at that spot is concave up. So draw something concave up. And if I draw something concave up, now I can see that that 3 is going to be an absolute min. So the only other thing to do would be to find the Y value that it is paired with. And if I do that, again, for Y values, I always want to plug 3 into the original function. So I want to plug 3 in for x in the original f of x. So I'm going to plug that 3 all the way back into that original function. And if I do that, I get negative 17. I'll let you check that on your calculator. Okay, let's work through one more example just so that you have one more example to work off of. If you feel like you got it, then X out of the video and get started on your homework. All right, so the second example, I'm going to work through the exact same steps, only this time notice that when I go to find the derivative on that second term there, I'm going to want to rewrite that. So I'm going to rewrite my function first as 2x plus 32x to the negative first. So I'm just going to move that x up to my numerator so that I can use my power rule. So my first derivative is 2 minus 32x, and when I subtract 1 from that exponent, I get negative 2. So I'm going to rewrite that derivative as I set it equal to 0. I want to drop that x squared back to the bottom so that I can solve that rational equation for x. So to solve a rational equation, we're going to multiply everything by x squared. So I'm going to take this entire side of the equation and multiply by x squared, and I'm going to multiply that 0 by x squared. So when I do that, I get 0 on the left. And now don't forget on this side to distribute that x squared to both of these terms. So I'm going to get a 2x squared. And on the second term, the x squareds would divide out, so I would just have a minus 32. Okay, now we can set that equal to 0 and factor out a 2. And then I can factor that as the difference of two squares, x plus 4, x minus 4. And now I finally have my critical values, -4 and 4. Now, once again, I want to make sure that I compare those critical numbers to my interval that I was given. And the interval I was given was x had to be strictly less than 0. So that means my 4 gets omitted. So the only critical number that I have to test is -4. And because I only have one critical number, I need the second derivative test. So now I'm going to find that second derivative. So my second derivative would be, and again, I'm going to work off of that first derivative. So the derivative of 2 is 0. And then the derivative of this -32x to the -2, when I bring that -2 out front, it's going to make that a positive 64. Subtract 1 from the exponent, so it gives me 64x to the -3rd, which I then want to rewrite with a positive exponent, so 64 over x cubed is my second derivative. So now remember what we're doing with that second derivative is we want to plug in the critical number that we found, and that critical number we found was -4. So I want to plug in -4 into that second derivative and determine if that's going to be positive or negative. So again, I don't care what this value is, but I do know that -4 cubed is going to be negative, and 64 divided by a negative value is going to keep it negative. And so remember what a second derivative being negative means. It means that my curve at this spot is concave down. So what does that mean? It means that I have determined that my -4 right here is an absolute min. So all I need to do to finish up then is to, I need that function in my picture, I need to figure out my y value. So my absolute min is going to be -4 comma, and we want to plug that -4 back into the original function. So I want 2 over -4 plus 32 over -4, and that's going to give me a y value of -16. Okay, so you've got two examples of each type, closed interval, open interval. That should give you enough to go on for you to complete your homework. Make sure you email me if you have any questions. Whew.